Where is screen sharing now? Screen share, okay. Start sharing.
Okay, we can see the details now.
Okay, great. Thank you. Apologies for the difficulties. I don't see the crowd. Maybe you can turn your computer so I get the reactions. Hello? Chris?
Yep, okay. Yes, so basically, unfortunately, we are using my laptop to connect, so you can't see the participants. You have to see me for now.
Right. You cannot turn it, right?
Well, I can turn the laptop, but then I can't follow.
Okay. This is a presentation for this first hour. We will go through the concepts, the basic concepts for neural networks and deep learning. So there will be no coding, and then the next hour at 5, we'll start getting into PyTorch around the basics. So we will see how to install it, how to run it, what data structures it has, and how to make autograd work, how to run on the GPU. So this is the layout of the 4 lessons. The first is neural networks and backpropagation, which we'll do this hour. Then we'll go into PyTorch basics later today. And tomorrow afternoon, we'll see neural networks created with PyTorch, some things related to training them, the essentials. And then we'll get into, this will be, the last part will be more an introduction for your hackathon. So how to load the data that you shared on the hackathon repo, and how to build a basic PyTorch network that will do something with that data. So that's the main layout. I don't know if there are questions. Please, come up to the screen. If you think things are getting too fast, especially when we will show the code, please stop, and we can get back, of course. Okay, so we can start. So a couple of words on who I am. I'm currently working at Orobics, which is a company based in Italy, in Bergamo, that does engineering of systems with some broadly named AI inside. So we work mainly in healthcare manufacturing. So healthcare, we do medical image segmentation, mostly analysis of clinical data. Manufacturing, we do a lot of quality control on industrial lines, process optimization, and we have other projects. We worked on a game last year, so we have different sectors we're covering, but mainly with techniques that we will talk about today. And TensorWorks is a spin-off based in the US that we founded last year, that is building things like data version control systems and deep learning runtimes. So it's more focused on the technological part. So we're developing a few technological open source projects that kind of complement the tool set of people working with deep learning, and recognizing that these techniques, like the ones we will talk about today, are moving from the purely data science realm to the software development realm. So we will need, as developers of future systems, we will need tools beyond just PyTorch or just TensorFlow to build software that has behavior that depends on what examples it saw in the past. I've been contributing to PyTorch core, especially 2017, 2018. So I was an early contributor, and then things got way too quick for me to keep up. So I gave my contributions for a couple of years, and in the meantime, I co-wrote a book that you can find online for free in the Facebook, the PyTorch website. And the final version is coming out. So the Facebook version has just a part of part one, and there are 3 parts in the full book. And with aerobics, I'm a project partner in ESCAPE, in the European project on software infrastructure for physics and astrophysics. This slide deck will contain mainly figures from the book, as well as some slides from a course that has been published online and has an open source license. So since we're in a physics context, oh yeah, and in the past I contributed to GammaLearn, which is a project within the Asterix Greater project with ANSI, where we worked at creating neural networks, deep learning model for Cherenkov telescope arrays. So we implemented, for example, convolution layers for hexagonal lattices and so on. Okay, so many of you already use deep learning, so there's no need of reinforcing this. Deep learning essentially is a way to approximate input-output functions where the inputs and the outputs can be quite far from each other. So you can build classifier regressors and generative models in an efficient way. There have been several examples of the use of deep learning in physics, and this school is basically aimed at increasing the knowledge of machine learning and deep learning workflows, technologies, methods for the kind of research you do. But in order to read a paper on deep learning, or read a deep learning paper or an applied deep learning, how deep learning was applied to a particular problem domain, at first it can be daunting because there's a lot of terminology there that is not really transparent. One has to go back to the basics and really learn what are the building blocks. Fortunately enough, the building blocks are quite easy to understand. And so with a few hours of well-directed study, one can already start parsing what the papers are saying, and then by practicing, you can get a grasp of a lot of the things that seem obscure at the beginning. And this is the exact process I followed, because I come from a biomedical background and engineering background. And so I got into deep learning in 2014. So relatively, not late, but not too early to the party. I'm not originally a data scientist. And so this is the process I followed too. So where deep learning comes from, this is a very crude view of the fact that software has increasingly been built from different approaches. One is a rule-based, so a lot of rule-based systems, basically all the software we know right now, except a tiny fraction of it, is based on rules. As a matter of fact, this slide incorrectly says that machine learning and deep learning are relatively recent. In fact, the first neural network models were originating from the 40s and 50s. So they have been around for a long time, but this slide is mostly were concerned about the actual adoption in the real world. So rule-based systems essentially are systems that are built with rules that are created top-down. They're hand-designed, and so their abilities are map one-to-one with the worst programmer that implemented them. So there's a weak link that that links the ability of these systems and the ability of the people that worked on it. While going down with classical machine learning is the adoption of models that can classify or perform regression on features that are pre-extracted with hand-designed feature structures. So, for example, if I have to identify people, I will look for vertical people standing for vertical lines and something looking like a circle on top, very crudely. And if I can kind of extract these features from images and encode them in a numerical vector somehow, for example, how many vertical lines there are and how many of them have a circle on top, then I can take those numbers that are pre-digested from the feature that I created and pass them through a model that can assess the probability that what I'm looking at through these features correspond to the content I'm expecting. And deep learning extends these concepts by going backward one step and say, I have an end-to-end way of building a big model with comprising of several steps that are optimized as a whole, so that I can go from raw input to the output directly. So basically, the features are extracted during the model optimization process rather than decided beforehand. And this unleashed, this depended on the availability of data, on the availability of computing power, and on the discovery of a few tricks to make these things that are basically greatly over-parameterized nonlinear models to start solving more and more complicated problems. So the paradigm shift is really from handcrafted features and a learning machine that takes these features and produces an outcome to something that it's a bit more black boxy, but takes data in raw form and learns how to extract those features into, or to digest the raw data into intermediate representations that step by step become closer and closer to the outcome, and so that then the machine can produce the outcome. So what is the mental model when we apply a deep learning model? Is we start from a network, which is nothing more than a calculation expressed in graph form, and we'll get a lot deeper in this concept throughout these 4 hours that we'll spend together. And through a training loop, which is an optimization step, we optimize the parameters in this model based on what is the output compared to an expected output on a batch of inputs. So based on the error that we're making, the parameters of this model will be optimized so that we'll end up with a model that is trained, which is nothing more than a program that can be encoded in a subsection of multiplications and nonlinear functions and additions and so on. And it's actually possible to export these models in binary form, like if they were executable, and put them in production in a runtime. And this is what we do all the time at work. Typically, training a model is computation intensive. So if you can get access to one machine or a cluster of machines, but especially with accelerators like GPUs, graphical processing units. That is the basic survival kit for somebody doing deep learning. So if you do deep learning, don't try to approach it with a CPU only computational resources, because it will, unless the data is very small, which begs the question why you're using deep learning, it will be painfully slow to train deep learning models on conventional hardware. Luckily, as we will see, you can access free GPU resources through Google Collaboratory. So you can run trainings, maybe not for days, for a few hours on free GPUs online. Production servers, on the other end, they have much lower computational demands. For example, you can run, depending on the rate, the frequency at which you have to run a model, you can run it on the CPU. We have models in production that run on a Intel i5. They're not big ones, but they do something useful, for example, in industrial settings. Or you can use GPUs, consumer or adapted for inference, or edge devices like the Jetson, NVIDIA Jetson, which is a GPU for embedded devices. So what is a neural network? Basically, it's some sort, you can think about it as a function that performs some compression. So given some piece of information that has a lot of degrees of freedom, is something that a neural network can encode those very many degrees of freedom in a lower number of degrees of freedom, up until the point where you can make a decision based on a vector of numbers, whether what you're looking at is something or something else, or you can make a prediction in terms of quantifying a physical property of it, for example, in a continuous manner. The vector of numbers in which the input is encoded is called intermediate representation. And what produces those intermediate representations are those red dots that we'll zoom in a second, which are very, very simple computational units. And the parameters that go from input to output at each layer are usually initialized at random, so you don't know them at the beginning, but they are optimized as the training proceeds. So how they are optimized, we will see it in detail, is based on errors evaluated on a so-called loss function, which is an error function that the optimization process tries to minimize. Of course, all of you have done nonlinear fitting or even linear fits in their scientific life, and any one of you who has done something nonlinear, which is virtually a lot of you, also knows that having a nonlinear fit work properly sometimes is tricky. You have to fiddle with parameters and so on. So how can something having millions of parameters actually converge on something that you want? That's a pretty fascinating question, and it has to do with the shapes of the function that compose these red dots. So by taking a particular analytical form, and these models can be actually optimized even if they are over-parameterized. And it's an active area of research to understand why exactly these mathematical constructs can be optimized this way. I mean, it makes sense from on the surface, but going deeper, it's a non-trivial thing that we can do what we can do with deep learning, and it's not fully understood yet. Okay, so tensors, we are in front of the physics crowd. So when you go into deep learning with TensorFlow, PyTorch, all these frameworks, call tensors something that you guys don't call tensors usually. These are just multidimensional arrays. So when you see tensors in the documentation, you don't have to think about tensors in vector spaces and so on, but you have to think about tensors as just multidimensional arrays. They're just a generalization of a matrix. So this is a bit of a misnomer, but it has permeated the practitioner community. So that's what we have to live with. So in general, the data structures that you deal with in deep learning are multidimensional arrays. And the learning process, zooming in a little bit closer, is you have inputs on this side. Inputs are coming from your training data set, so-called training data set. You have a bunch of desired outputs. This doesn't happen all the time. Like I'm describing a training setting which is called supervised set training, that for which the outputs are actually available to you. The desired output, for example, events from a telescope and the type of event that has been tagged somehow, maybe through a traditional processing pipeline, or maybe just because your data is simulated and you know where it comes from. Sometimes you don't have the luck of having annotations, and this is something for another time. But in the most common setting, you have the desired output that your neural network is desired to produce. And what the training process is split the inputs, shuffle the inputs, so there's some randomicity there. Take a batch of the inputs and have them produce a result, and then evaluate the error through the loss function, and somehow adjust the weights of the model so that they go in the direction of producing a lower error. And this is what the learning process is. It's just function fitting, essentially. And of course, validation, you have to perform validation on independent data. So typically you'll keep around two sets of data. One is for validation using during training. So at each training iteration, you will want to check how the model is doing on data that did not produce an error signal back, but you still monitor during training. And then a completely independent test set that you will only look at a very few times, so that you cannot possibly overfit on it, even by changing the parameters during training. Parameters related to training, like the step with which you change the weights, for example, they are all called collectively hyperparameters. So as practitioners, we will have to configure hyperparameters for training to happen. So let's zoom in the red ball that we have seen in the diagram a couple of slides back, and there's the neuron. Unfortunately, this is just something resembling a logistic function quite closely. So it's called the neuron just because ideally neurons in the brain probably have adopted a similar mathematical trick to be able to represent nonlinear functions very effectively, but it doesn't resemble a neuron at all. But from a first principle, a biological neuron is a cell that will have intake of ions, so that its charge its cross membrane voltage will be will increase as a summation. So there's a linear part there where each connection each channel will be taken in ions with a certain rate, and so the total voltage will be proportional to a weighted sum of all the inputs from other neurons. And then at some point when the potential will reach a threshold, then the neuron will generate an output down its axon. So this is represented by the nonlinear function. So the nonlinear function is there to saturate either low or high or both the output of that linear transformation, so that it from not producing anything, it starts producing some output. So from going to have an output that is saturated in a low state, it will go to a high state. And while it goes there, it will transition in a region that has a very linear-like behavior. So basically, in a population of computational neurons, there will be neurons that are initialized close to around their zero mean, and so many of them will behave like a linear function. So they will be they will be easy to train somehow, because it's easy to understand what happens if you change W, because it has a linear relationship between input and output at that point. And then at some point it will saturate, and so any change in W will not produce a change in output. So this is more or less how the neurons in the brain work, and how the computational neuron here works as well. The nonlinear function is something that most of the time is not learned. So all you learn is the things in blue. It's the linear transformation, and the bias. B is the bias, so the constant that you add to it. This will basically most of the time be what your neural network will optimize, what the learning process will optimize. And the nonlinear function is there just to provide the mechanism that I explained before. So you can replace the nonlinear function with other nonlinear functions. It doesn't make a lot of difference. Of course, it makes some difference. Some of them are better in certain circumstances and some in others, but and there are a collection of them. But it's really not inherent to the fact that the fact that it's there, it's enough to have the neural network model evolve towards a better performance. Actually, there was a work that was presented 2-3 years ago, in which a researcher made a neural network without any nonlinearity. Of course, a composition of functions, or linear functions and nonlinear function, but on a computer, if you work with very, very small numbers, you have rounding errors. And so they were using rounding errors as nonlinear activations. So any kind of nonlinearity at that level could be employed to make a neural network capable of representing nonlinear functions globally. And this is a breakdown of 3 very popular activation functions. You have the hyperbolic tangent. It goes from -1 to 1. Sigmoid from 0 to 1. The derivative around 0 is, in the 2 cases, is for a certain range of the domain, is approximable with a line. And there's another one which is called ReLU, rectified linear unit, that is simply 0 for the argument lower than 0, and linear, and the identity for the argument being positive. As you can see, they're very different, but they all work in the end with different characteristics. Okay, so what a neural network looks like in practice when you start arranging these units, so the linear part and the nonlinear part, and stack them one on top of the other, is that really you are composing a function. So this on top is nothing but a neural network expressed as a mathematical expression. So you have a neuron whose output gets as the input of another neuron, and so on. In this case, to make a parallel between the bottom figure with the graphics of the layers and the top expression, you have to consider that W1, B1, and X will be vectors. So, sorry, W1 will be, so B1 and X will be vectors. Okay. And you can see that the learn part is the linear part, and then the activation kind of saturates the response. The activation is not learned, as we have seen. So basically, the optimization process will push both the weights and the bias towards making the output, so the argument of tan H in this case, move so that it will be in the learnable range, so around 0, independently from what the input is. So if you have a the input that is very far from 0, in order for that unit to learn, to produce an output that is meaningful and a signal that for which the error can be evaluated, that argument will have to be moved around 0, because that's what the nonlinear activation function is. So the tendency, of course, is to make it so that the inputs are normalized, so that they are themselves around 0 and they're not scaled too broadly far from unity, so that the W1 and B1 are easy to obtain and to find. So this is the reason why usually you're told to normalize your inputs. And as we will see not in this session, but later on, there are also techniques to ensure that what comes out of each layer is also normalized properly. And this helps the training process a lot. Okay, so in a bit more mathematical terms, we have the neuron can be called the logistic unit, where the sigma there is just a nonlinearity that can be chosen, and W it's a number, X is a number, and B is another number. Where X, if you add more than one feature, then X and W will be vectors. These units can be, although composed in parallel. So as we saw in the previous slide, okay. So W at this point becomes a matrix, and so you really have a linear transformation plus a constant going through a nonlinearity that produces another vector that has dimensionality Q. Okay. So this is the representation of just one layer with many units. If you move and start stacking the layer and put in another layer, so the inputs of the first become the outputs of the first become the inputs of the second, then we have this kind of arrangement where you have the first H0 is X, the input, and then you start producing the output of the first layer, and then the output of the last layer. And you can represent all this machinery with theta, which denotes the parameters of the model that you wish to optimize. This is called a multi-layer perceptron, also known as a fully connected feed-forward network. So it's fully connected because the output of a layer goes into the input of every unit of the layer. So it's not sparse at all. It's fully connected because every layer goes into all the neurons of the next. And at the bottom you have another representation where the red balls are what need to be optimized. And this is actually pretty close to the representation that frameworks like PyTorch have internally. This is really a graph, an acyclic directed graph. Or it can even be cyclic in more complicated model. It represents a computation. And when you save a model, so for example, the ONNX format is a format that describes this type of computations and has a room for parameters. And so if you describe this as a sequence of operation and you have a runtime that can execute these operations become the program, and you can it can be portable between runtimes. So what does it mean to classify something? So if you have, I don't know, in Chernov's arrays, telescope arrays, you have protons and gamma events to classify. So what does it mean to classify? Well, you can pretend that the output, or you can induce the network to produce something resembling a probability. A probability is something that sums up to 1. And so there is an operation that, given the output, given a vector, can produce another vector, element by element, for which the individual elements are between 0 and 1, and it globally sums up to 1. And this is the softmax operation. So basically, for classification, a neural network will have the same structure as for regression. So produce a vector of numbers in output. But then at the last operation which you will do, you will convert those numbers into something that simply is compatible with the definition of probability. So it's just imposing that they are between 0 and 1 and they sum up to 1. And in the case of a regression job, you can skip the last activation, the softmax, and you have unbounded output values. Okay, so what induces these networks to assume a certain behavior, like regression or classification, apart from the fact that we can impose that numbers at some point sum up to 1, is the learning process. So you have to define a loss function, and the learning process will drive the network towards minimizing that loss function. And the way we do it is not through very sophisticated optimizers, but actually, well, there are families of optimizers that, but in the end, most of the times, there are a couple, 2-3 optimizers that practitioners use. And one of them is stochastic gradient descent, which is the most vanilla one, but it's actually the one that you use when models increase their complexity. They're the last resort. But it's the simplest one, but it's also one of the ones that works in a very reliable way. So how does the learning process work? You can define a loss, as we have said. For example, for regression, you can choose the mean square error or cross entropy for classification, and we can look at those later on in the day or tomorrow. And so you define this loss function calculated over the m samples, for example, of the inputs. Usually we train on batches, as we will see. So you have a training set that is composed by thousands or hundreds of thousands or millions of elements, and we will shuffle them, take a batch of them, so a small group of them, pass them through the neural network model, and then evaluate the loss function for each of them and sum it up and have an average value of the loss. And then we can also, following that, we can also have some kind of regularization. In this case, it's L2 regularization. So you take all the weights in the model and sum them squared. And this is a regularization that tends to keep the weights as low as possible. And then all you do in the end during the learning process is compute the partial derivatives of the loss with respect to each parameter, which is a gradient vector of millions of elements potentially, and simply apply an update to each weight so that the new value of the weight goes in the direction of the descending gradient. Of course, the step it's very crude, as you can see, and the step, the learning rate, called by practitioners, is just a relaxation factor. It's alpha, and it dictates how quickly you will change the weights, and typically it's quite small, as you can imagine. So I don't think this needs to be further described, but gradient descent, you use local linear information to move towards a local minimum. Now, the problem of local minima and global minima in deep learning is probably not a very interesting problem. So the topology of loss functions with this super over-parameterized models is a very interesting research topic. And typically, we don't want to find the global minimum. We are okay finding a broad, flat, local minimum area, and we're content with that. The problem of finding a global minimum, it's probably not very interesting in deep learning in general for many reasons. One of them being that if you find a global, or what looks like a global minimum that has very steep walls around it, it's probably an effect of you are overfitting your training set. Your goal should be to find an area, a relatively large area of low enough and flat loss function. Okay, so we talked about stochastic gradient descent. What does stochastic come from? Well, it's the stochastic portion of it. Well, we've seen gradient descent, but why stochastic gradient descent? We said before that we start from a big training data set, and we take a subset of the data set, which is called the batch, the mini batch. So we take like 100 cases or 50 cases out of 100,000, and we evaluate the gradient vector from that sample. And that gradient that we use to update parameters, of course, it's a very partial estimation of the overall gradient computed over the whole training set, or even beyond that, right? So you can, if you shuffle the choice of the mini batch out of your training set, then you will have a randomly inaccurate idea of what your actual gradient points to. But that's actually beneficial to avoid getting stuck or having an overly constrained and expensive optimization process. So by having a poor approximation of your gradient, that's where stochastic come from. So there's no term like I estimate the gradient and I inject noise in it. The stochastic part of it is just how I randomly choose my training samples on which I estimate the gradient and the loss and the gradient of the loss. Okay, and then of course the learning rate is very important because you don't want to make your training diverge because you take steps that are too large. And what does it mean taking steps that are too large during optimization, during gradient descent, is that you take steps for which the linear approximation no longer holds. So you find yourself somewhere else in the loss landscape, and then you didn't go in the approximating along the approximating hyperplane or manifold. How do you do this in practice? Is you resort to high school maths. Remember the shape that the functions had when we built our deep learning or our neural network. They were all linear functions with nonlinear contained in nonlinear functions passed on to functions of the same size. So it's a composition of very simple functions that for which we know how to compute derivatives. So basically, when we have to estimate the gradient, all we can do is take our loss function that will be differentiable almost everywhere, just like all the functions that we use here, and then just using the chain rule, compute the partial derivatives down to the parameter that we are interested in, which is all of them. So we will have to compute partial derivatives through the whole model millions of times to get the update vector that we have to apply to our parameters to get the new version of the network. And we have to do this hundreds of thousands, millions of times. So this is a very computation intensive operation, but luckily it's an operation that can be parallelized and be optimized using automated differentiation engine like PyTorch or TensorFlow or Theano before them. So if you look up into papers, what backpropagation really is just the chain rule. The chain rule applied to a model that has a shape like the ones that we have just seen. So the forward, this is just terminology. The forward pass is using the model to produce outputs from inputs. The backward pass is applying backpropagation. It's a misnomer, but you go from the first term of the chain rule, which starts from the end, from the loss function, and then go back computing the partial derivatives. That's why it goes backward. Okay, so I talked before about training set, validation set. Usually you want to optimize your model on a training set and keep a validation set of independent samples around so that you can take the trained model and look at the performance. So in blue, you have a line that shows you how your loss function hopefully will go. And in red, you see how your model will perform on independent data, computed through the same loss function. And you see there are different behaviors of your loss. And this is basically 90% of your job is staring at these plots at hours intervals and then tweak something where you see something going wrong. And how you see that something is going wrong is by looking at the behavior of the loss. In the case A, nothing is happening. So the loss is always up there. The validation set and the training set behave the same way. Basically, the loss is the same at the first iteration as it is at the nth iteration. So basically what it means is that the errors that backpropagate do not improve the model. So the changes you're making to the parameters are not improving anything in your model. So there must be something wrong with it. With either there's a bug in your code or your data is absolutely random. So you cannot predict the output given the input. In the B scenario, you see the training loss that goes down, so it decreases, and the validation loss that increases. And this is a phenomenon that happens all the time if you're not careful. We said that in deep learning sometimes we have many more parameters than we have data. And so this is a typical example where you will overfit. So your model will start learning your data and just your data. It will not generalize to data that is similar to the data you have, just because it will memorize the data inside the parameters, essentially. And you can recognize this effect by seeing that at some point, the error that you make on the validation set goes up, and the error you're making on the training set keeps decreasing, and eventually it will go to 0. If it doesn't go, so any sufficiently large network will fit anything you throw at it. So if you take a network, run a training loop, and you keep making your network larger, if the data is not completely bogus, or you will see that the network will start learning your examples, but the validation set, the performance on the validation set, will get poorer and poorer. What this means is that the behavior of your model in between the training point will be ill-defined. What you want to do in this case is to try to either regularize or do something so that the behavior of your model in between training points has a similar behavior than on an independent data set. So sometimes you will see that the training set doesn't go exactly to 0, and this might be due to problems in the annotations. So problems in your desired output information. It's called the ground truth. So if you label training and validation in a certain way, and if you label protons and gamma events in telescope array images, and maybe the data set contains duplicate inconsistent data, like a duplication of events that have been labeled both proton and gamma, you will see that even if you enlarge your network, the loss function will not go to 0. The validation loss function will not go to 0. And typically, this is what we will do at the first, like when you start working on data. Decide the network architecture, run a first training, and then start increasing the capacity of your network, so the number of parameters, so that your network can actually overfit your data. It means that there's hope in having a network that will learn your data while not overfitting. And then once you have reached overfitting, then you start making your data smaller, your network smaller, so that the validation and training losses resemble each other. So you can decrease the size of your network. You can put regularization like L2 regularization that we have seen, or do other things that we'll talk about to try to keep your validation loss with a similar shape as the training set. And the ideal situation is not C actually, but it's D. So you have to overfit a bit as a best practice, rather than have validation and training be completely overlapping. Okay.
So.
Okay, sorry. Okay, so maybe the time has finished, or are there questions?
Do we have any questions? No, we don't have any questions. From our side, if you want to, I can see that you are on page 25, and there's like 10 slides left, 11 slides. From our side, if you want, you can continue, because we have another session scheduled later. But if you're running late for your next meeting, it's okay, we can schedule 4 or 5 p.m. So you tell us what's best, what works best.
I don't know if you're okay, we can go on with this and we can keep the next one more interactive.
So let's keep going then. Let's keep going with this.
You agree? Okay. If you have, I know this is all very basic, but if we lay down the basics, then it will be much easier later on.
Quick question before we move on, please.
Yeah.
So could you explain again the differences between C and D, please? The losses there?
Yeah, I actually didn't go into details. So C is a situation in which the performance in your training set and the validation set are completely overlapping. While in D, the performance of your training set and validation set are a bit far apart, but the validation set has a bit of an offset compared to the training set, meaning that the trends are similar, but you still keep your validation set with a worse loss a bit. So in general, it's good to have a model that has some ability to retain some information about the training set. So C is ideal. Okay, so if you can do this, then great. But probably if you do C, the scale on the y-axis in C will keep your loss. So you can achieve C by having a simpler model. But in order to achieve C, you have to accept a value of the loss that is higher globally, right? So if you make a model very small, like a logistic regression to the limit, logistic regression on complicated data, the model itself will not overfit, but it will not fit very well because it doesn't have a lot of capacity. And in that case, probably loss and validation will be similar just because your capacity is not enough. So when you see this effect, it's actually better that you try to overfit a bit so you know that you have enough capacity to memorize, so you're not underrepresenting your data, but at the same point, you keep your validation curve in sync with your training curve, although with an offset.
So basically, if I understood, so C is saying that your model is too simple, basically?
Yeah, it might say that.
Or at least one possible reason. Okay.
Yeah.
Okay, that makes sense. Okay. Thank you.
Yeah, this is quite like this is important because it's the current practice. How, as a rule of thumb, how deep and how wide should my model be? That's the number one question, right? And sometimes it looks like really a shot in the dark. What is it like between the two? And as a rule of thumb, capacity, so width, how many neurons you stack, is the ability of the model to memorize more things. Yeah. So by increasing capacity, you will tend to have these effects. But the ability to actually learn what is in there, so to go from an A-ish behavior to something that goes down, resides on the depth. Because the depth, it resides on the depth if the data set has some hierarchy in it. For example, if I need to study, to identify the eyes of a person in a complex scene, I will need many operations to get me from a picture to the actual eyes of a person. If I have to identify a shape in a white background, if it's a round or a circle or a square, I don't need a lot of depth in there because the information is not very hierarchical. Yeah. So I don't need many steps to get there. And so basically, this is a very, very crude rule of thumb, but that's a thing to keep in mind.
Okay, thank you.
Okay. 1 second. Okay. I'll need to go out in 10 minutes. So I think we can make it 10, 15 minutes. Okay. And then on top of what you have just seen, we have a number of other things that actually make things work, which are tricks that are counterintuitive at the beginning, but they can really be very important to be able to train these objects. And by being able to train these also means mainly means avoiding overfitting in the end. So they are all forms of regularization, because you can have regularization by constraining the value of parameters to be bounded or to be as low as possible, but you can also induce regularization by randomizing things. If you randomize things, the network will be forced not to memorize things too much because it doesn't have the opportunity to do so. For example, dropout is what you see in the figure. Dropout at every iteration, which means it changes at every iteration. You decide that you will set the activations to 0, a fraction of the activations to 0, which means that that a neuron will have I don't know, 5 inputs in the previous iteration, but then a different number of inputs, or always 5 but other inputs from different neurons in the next iteration. The level of dropout can be dramatic, so you can set to 0 like 30-40% of the activations at each iteration, and this will help regularizing the behavior of individual neurons, because they will tend not to be able to memorize the input. Best norm is another technique by which you renormalize around 0 and 1 standard deviation the output of a layer for an individual mini batch. And this also helps regularization because it keeps individual neurons around those points where the nonlinearity is linear, even if you don't apply a strong bias or a strong scaling to them. So it's easier for the network to find the right, to not saturate individual neurons. Batch normalization is also important for, so it can also be a replacement for dropout. So the paper that presented batch norm said that with batch norm, you don't need dropout and regularization. So it can act as a regularizer. And the reason is that the batch normalization will be applied on an individual batch. So, and since the individual batch is random, then basically all the patterns you see in the network will never be repeated, because each individual sample will end up into its own mini batch that will change every time it gets sampled from the training set. So the actual input will get rescaled every time in a different way. Stochastic depth is something that hasn't gained much popularity, but it's there anyway. So decrease and increase the depth of the network. Noise injection is a practice that you can do. After all, dropout looks like noise injection within the network itself, but basically you can also inject noise in the image itself, or in the input itself. So if you have inputs, and every time you see an input, you also superimpose a random noise on top of the input, then you will have the training process achieving better generalization, because you never present the input at the we said before that we want to improve the behavior of the network in between training points in some ideal space, embedding space of the input. And this injection of noise kind of hints at that. You are requiring the network to recognize neighboring situations around your training set point. Data augmentation is a form of the same thing, which is modifying, for example, in terms of images, modifying input images by applying transformations to them, like rotations, flipping, scaling, shearing, or B-spline deformations, in a way that it's consistent to what you might find in the wild in data points that you haven't seen. And it's a form of the same thing. An interesting property of dropout is that you can also use it to do advanced things like estimating uncertainty. So one thing that neural networks are not very good at is telling you if they are uncertain about something. So if you train a network to work between zero on handwritten digits between 0 and 9, and you present it a cat, it will tell you that it's a 5 with 99% probability. And this is a complementary effect compared to overfitting, and it's called overgeneralization. And it's an effect that we're actively studying at Eurowix, because it's one of the most important things when you go in production is getting a I don't know from a model instead of getting an output. For example, in a quality inspection line, if there is a defect that has never been seen, or a good part that exhibits features that are different from usual, so out of distribution in technical terms, you might want your network to tell you about that. Dropout can be used for producing a metric that approximates the information, because you can make many inference steps. Once the model is trained, you can apply dropout, which is you can create different versions of the same network with different connections. And since the network was trained on with dropout activated, the network already compensates for this, but it will produce. So it was trained to produce for the same input a correct answer, no matter what the dropout was. But if there is an out-of-distribution sample, it's been demonstrated that if you use dropout during inference, probably the output of something that has never been seen after dropout can have a greater variability. So if you apply one round of dropout to the cat we were mentioning before, sometimes it will tell you it's a 3, sometimes it's a 4, sometimes it's a 6, for the very process that happens during overgeneralization. So you can recognize by fudging with the weights through dropout and asking the same question again and again, if the training sample, if the sample that you're examining has been seen during training, or it's in the same distribution, then the network will behave consistently. Otherwise, it will have a greater variability. So this is a very interesting effect that we're using. So probably it's better to stop here because time is running out for me, but we can go quickly and then move on to the interactive part for the rest, because we have to introduce convolutions, which is another linear operation that you can use, and is particularly interesting for anything that is continuous in space or time. For example, images, but also fields of physical properties or signals in time. So this is a very important part. But in the meantime, if you have time, or we can look at it together, there is a nice playground in the TensorFlow website that lets you play with neural networks on toy datasets. We'll see a different one on convolution on neural networks in the next hour. And this is great to experiment with the effect of different nonlinearities, different learning rates, different optimization schemes, different depth and different width on toy problems. So I encourage you to play with this, because it basically it's a tiny model of what you will find yourself doing with longer time scale when you have a full problem. Okay, good. I hope this was useful so far. I'm sure many people has already heard these things over and over. So I hope it was not boring for them. And if there are questions, I can answer them now in the 2 minutes that I have, or we can resume later on.
Do you have any questions? Yes, we have.
Earlier on, you mentioned.
Wait, can you come closer? Because we won't hear you.
So earlier on, you mentioned PyTorch.
Yes.
What specialities or does it present compared to TensorFlow?
Yeah, we can talk about that in the next hour, but I think I've used TensorFlow a bit and PyTorch for the rest. I think both of them are great. One of the advantages of PyTorch is that it's a lot simpler to know well. TensorFlow is a bit more googly, so Google like to do things in an elaborate way. So let's say at the beginning, the striking difference was that TensorFlow was a static graph framework, and PyTorch was a dynamic graph framework. What this means is that in TensorFlow, you had to build the computation graph that we have seen in this lesson, and we'll see it in the next, especially. So the concatenation of nodes for operations and so on in a static way. So first you define the graph and then you run it backwards and forward. In PyTorch instead is so in a way it was a language on top of Python, and so everything was fine when you were building the model, but then when some error would come, you would get an error in the context of that language. So error messages for TensorFlow were kind of more harder to parse and so on, to understand. While PyTorch was one of the frameworks and the one that won among those frameworks that proposed a dynamic graph where each operation was eager. So it looked like working with NumPy. And so you would build a neural network by executing Python commands, and they would execute immediately without building a graph and then executing, but executing as you were going. And so it turned out that this model allows for more dynamic neural network models, but most of all, it has a more user-friendly and behavior when something goes wrong, and you can build more complicated models out of it. And at the same time, it's quite simple. So the API for PyTorch is simple, while TensorFlow, it was a bit harder. So there was Keras on top, but sometimes Keras wasn't enough. So you had to go into TensorFlow to build certain layers and so on. Since then, TensorFlow has evolved and developed a dynamic mode. It's called eager mode. And they are right there in the transition. So TensorFlow 2 introduced a programming model that is really close to what PyTorch has, but PyTorch at this point is more mature. So they're both great frameworks. To me, to my personal taste, PyTorch is a bit easier to grasp and easier to work with. And it has a very nice backward compatibility. So if you developed a model with PyTorch 0.2, now we are at 1.4, and probably you have to spend like 5 minutes adapting the code, but it's really minor things. And this is not necessarily to do with TensorFlow. Having said this, they're both great. And I would advise to use the one you know best because it's really a choice between two great tools.
Okay, thank you.
Yeah.
Do you have any other questions? No. So thank you, Luca, for now.
Yeah.
We'll see you in an hour and a half. Okay.
Exactly. Okay. Thank you. Bye-bye.